lastly, we have Will, who's a third-year student at my Alex. Who's also former D1 athlete and D2, D3. Okay, and he's going to be talking about some work, drawing work that was hearing at some upcoming stuff.
Hey everyone, I'm going to be talking about my paper with Ellis called Spanning Tree Embeddings Are Not Much Harder Than Hierarchical Partitions. So a spanning tree embedding is pictured on the left of the screen here. Basically, you have a graph and you just want to find a subtree that spans the graph and in some sense captures all the distances in the graph well. And we care about this because it's generally easier to solve a lot of problems on a tree than on a graph. And so then a framework that can be useful to solve a lot of algorithmic problems on a graph is that you embed the graph into a subtree, and then you can solve the problem on the tree, which we want to say is easier, and then you somehow recover a solution to the original problem. But in this paper, we're just going to be talking about the first step. How do you embed your graph into a subtree? So first of all, there's one pretty big problem with this. If you just take a single tree, it's not possible to capture all the distances in your graph well. One way you can see this is to consider a cycle. Any spanning tree of a cycle, you're just going to remove one edge from the cycle, and then the vertices on either edge of that edge have to go all the way around the cycle, so their distance is going to be n instead of just 1. So to get around this, we have different notions of subtrees that are actually useful. One is called a subtree cover. So that's just a small number of trees so that all distances are preserved in at least one of the trees. There's also probabilistic subtree embeddings. Here you want a distribution over subtrees so that in expectation the distances are preserved. There's also Ramsey trees. This is going to be a single tree where many of the distances are preserved. Some are not. And lastly, there's a universal Steiner tree, which you can think of as a single tree where for any set of terminals, it gives good results for a Steiner tree. Don't worry if any of those things don't make sense. The point is there's a lot of different ways you can try to embed a graph's distance into a subtree. One kind of annoying thing is that there's not a particularly unified way of doing this. All these things have different objectives, and the way of creating a subtree is sort of ad hoc for all of them. So one of the main observations of our paper is that it's often easier to embed graph distances into something called a hierarchy of partitions, and I'll tell you what that actually is later. So it's easier to do that than to embed it into a spanning tree. So then our goal is to say, well, if you're able to embed your graph into a hierarchy of partition hierarchy, can you then also embed it into a spanning tree for free? And so that's going to be what this paper is. We just say, yeah, in some sense, this is easy, much of the time. Oops. Okay, I've been talking about partitions a lot. Probably a lot of you know what that is, but it's just given a graph, you want to break up the vertices, you partition them into sets. That's pictures on the left. Each blue shape is one part of the cluster. Generally, you want it to be the case that vertices that are close to each other are in the same cluster and things that are far apart are in different clusters. And so I mentioned before distances by hierarchies of partitions, and that's going to be closely related to the notion of the diameter of a partition. So there's strong and weak diameter. So here you can see we have one part of some larger cluster, only that one part's shown, and its strong diameter is going to be 3 because to get from U to V, if you travel completely within the cluster, you have to take 3 hops to get there. The other notion is weak diameter, where you're allowed to leave the cluster. So in this same example, the weak diameter would be 2 because to get from U to V, you can actually travel outside the cluster. We're going to be mostly concerned with strong diameter, which makes things a little harder. So I just wanted to point that out. Okay, and so now that we know what a partition is, I'm going to tell you what a hierarchical partition is. Basically, this picture on the left tells you what it is. It's a series of partitions that kind of respect each other's structure in some sense. But more formally, you're given some graph. Then a hierarchical partition is just going to be a sequence of partitions, so that the first one, C0, is going to be the singleton partition. So every single vertex is in its own partition. I don't have that pictured for clarity, but and then the final partition, everything is in the same partition. So that would be the red cluster in the picture. And then at each level coarses the previous level. So that's just the structure respecting property that you can see here, where like no blue vertex, like every blue vertex is completely contained in a green vertex. It doesn't like cross the boundary. And then lastly, we have the gamma growing part, which just says if you look at some part in the ith cluster, its strong diameter is going to be at most gamma to the I. So gamma is just some parameter of this hierarchy, could be anything, but it's gamma growing because in the ith cluster, everything's strong diameter is at most gamma to the I. And so then how do we actually define distance in these hierarchies? Well, if you see in the picture on the left, the distance between U and V, to find that, we're just going to look at what's the smallest cluster that contains both of them. You can see it's the green one. The green one's going to be the cluster at level 2, and so their distance is just going to be gamma squared. And that's what this text says. Does that make sense? Okay. So then the theorem that we show is that we can embed the hierarchies, the distance given by these hierarchies into a spanning tree with only constant loss. But we can only do that if we're growing by a sufficiently large amount. So if gamma is at least log of n, we can find a spanning tree whose distances are approximately the same as our hierarchy. So that's kind of the goal of what we want to do. We have some hierarchical partition that's been given to us. We can find a spanning tree, and so that's our main theorem.
Wait, what's the relation between gamma and just D sub h? Is that where gamma is?
Okay, yeah. So D sub h is the distance given by the hierarchy. I guess I didn't specifically say that that's what D sub h means. There's not actually a relationship. Like, as long as gamma is large enough, we just get a constant trade-off between the distances in the tree, like on the left side, and the distances in our hierarchy. And so that's a nice theorem, but it's a little specific with having to define these gamma growing hierarchies. So they give maybe a slightly mathematically nicer formulation of our theorem. We can actually get to work on laminar families. So a laminar family is kind of like a hierarchical partition, except we don't have these like rigid structure of each set has to belong to a specific hierarchy or a specific partition at some level. It's just a bunch of sets of vertices so that none of them cross each other. And then you can define distances pretty similarly. You just, for any two vertices, you look at the smallest set that contains both of them, and their distance is going to be the strong diameter of that set. And so then this top one is just the main theorem I presented a couple slides ago. And it's not so hard to see that given this theorem, a straightforward corollary is that given any laminar family, you can embed the distances into a spanning tree with O log n less. And you do that by just deleting sets from the laminar family until you get a spanning, a gamma growing hierarchical partition for gamma that's log n, and then you apply your main theorem. So I think that's a pretty nice mathematically pleasing result. So yeah, lastly, I'm going to try to quickly give a sketch of how our algorithm works. It's a top-down recursive algorithm. So we're going to be given first some part in the of the partition in the ith level. So that's going to be this big circle on the outside. And then if we go one level down, the partition of level I minus 1, and then just restrict it to C, that's going to be these smaller clusters. And then we're going to have a set of portals, which are just vertices in our graph. And this is a recursive algorithm, and so these are going to be inherited from a previous level of the recursion, but we know that they're going to belong to some shortest path, which means any two portals are close together in our tree. So to start with, our goal is going to be to get every child cluster to a portal as fast as possible. So for every child cluster, we're just going to choose an arbitrary representative and then take a shortest path to a child cluster that has a portal in it. And then our goal is going to be to take a prefix of all of these paths, and we're going to require that each child cluster only has a single path going through it. So like, for example, here, this one got chopped off because this path is going through it. And it's also going to be important that if you start at some child cluster and follow it all the way up to a portal, it doesn't have to hop too many times to get there. So it only has to take log n hops. Figuring out how to do this is probably the main technical contribution of our paper. We call it die-path aggregation. I won't go into it, but I think it's kind of nice if you're interested. And then lastly, we're going to recurse on each child cluster. So as mentioned before, like if we look at this one, the portals are going to be belong to some shortest path. So it's going to be the shortest path from that we got from this level. Then we recurse. We use all the vertices in the shortest path as portals. And then recursively, by just doing this at every level, we will end up building out the tree for that child cluster. And we get that at every child cluster, and then we get our spanning tree. That's pretty high level, but does it mostly make sense? Okay. So then, why does this work? Well, we need to be the case that for any vertices u and v, that the distance in our final tree is going to be at most gamma to the I, assuming that this cluster is part of the ith level partition. And so, see, in blue, we still have our shortest paths that we added. And then in black, we have edges that are added at recursive levels. So we just want to bound the length of this path, which is going to be part of our final spanning tree. And so some observations is that we of course have to switch between shortest paths sometimes. So like for you, for example, we get here, then we have to switch back over here. And we can only be set back. So like originally in the graph, we're at some distance from here to here. When we travel here, we can only be set back by the diameter of this cluster. And then also by induction, we can assume that this path isn't that long. And so since gamma is greater than log n, and we only switch paths log n times, these log n's sort of cancel out. And because of that, it's true that the distance from U to a portal in our spanning tree is at most O of the distance from our hierarchy. So like this distance. And then the same thing is true on this side. And then since our portals come from shortest paths, the distance is at most the diameter of the cluster. And so then adding all the distances together, we get our final desired distance, what we were trying to prove. Yeah, that's it.
Any questions?
Where would the part that you use gamma has to be larger than log n?
Right here, like, yeah, so like we might have to switch paths log n times, and like there's a price associated with that, both because you have to travel some distance, but then also because you might travel like the wrong distance, you might travel backwards. So,
This gets absorbed because U and V are like one level up.
yeah. Basically, you could lose like, basically you can like lose the diameter of your smaller cluster, and you can lose it log n times because you make log n hops. So then those sort of cancel out. If that makes sense.
Sure.
I guess that's a pretty high level, but
There's some kind of trade-off between the approximation, like because eventually you apply to laminar family.
Yeah, I guess there is a trade-off. Like,
then you will suffer. You won't have a constant approximation in this part of your proof.
yeah,
Instead, approximation.
yeah, something like that. Yeah, exactly.
Even now, you have smaller gamma.
Yeah.
Which may affect later when you apply it to some other problem.
Yeah, and kind of like the laminar family stuff kind of captures a lot of that trade-off. Yeah, I guess you can get the approximation ratio down to as close as like 3 plus epsilon as you make the constant in front of the log n arbitrarily high, I guess. But yeah.
Okay. Yeah. That's more offline.
Okay, yeah.
Let's think. We'll make all of our cases.